Okay, good evening to all. Today we are going to start the definition elementary matrix. So what do you mean by a matrix? When we say a matrix has to be elementary matrix, you have to apply exactly one elementary operation to the identity matrix. So if you apply or if you execute only one elementary row operation on the identity matrix, the resulting matrix is called elementary matrix. Okay, so maybe we can write the definition for elementary matrix. Okay, so definition. Okay, so definition. An elementary matrix, an elementary matrix. An elementary matrix is a matrix obtained from the identity matrix. Obtained from the identity matrix. Identity matrix. Maybe we call IN is a n cross n identity matrix by executing only one. By executing only one elementary row operation. Only one elementary row operation. Elementary row operation. So such a matrix is called elementary matrix. Okay. So for example, if you suppose you have to if you take identity matrix, if you suppose you are apply the first kind, what is the first kind of elementary row operation? You have to multiply a row by a non-zero number. Okay, so that is first kind. So for example, if you take 2 cross 2 identity matrix, I am taking 1 0 0 1, but instead of 1 I am multiply the second row by -5. Therefore this is an elementary matrix. So this is an example of elementary matrix because I am taking the identity matrix. So the 2 by 2 identity matrix, so 1 0 0 1. I'm going to multiply the second row by -5, we get this matrix. So I exactly applying only one elementary row operation. I applying here first kind. So we get this one. So this is one of the elementary matrix. Okay. Now I'm taking another one. Suppose I am interchanging two rows. That is the second one, right? So suppose if you take a 3 by 3 matrix, suppose I interchange the first row and then second row. Suppose I interchange the first row and then second row, we will get this matrix. So this is an elementary matrix. Okay. So interchanging two rows, I am applying only one operation, elementary row operation. Okay. Now please mute yourself. Now. Okay. Now we will discuss. Okay. Now we apply the third rule. So that means we have to multiply a row by a scalar and then we have to add to the another row. Okay. So we have to apply that kind. We will get some matrix. For example, if you take, I'm writing here 1 0 3 and 0 1 0 0 0 1. So this is an elementary matrix. Why? Because I multiply the third row in the identity matrix. I add with the first row. Okay. Suppose the the identity matrix is 0 1. This is the identity matrix. Now apply the third kind of elementary row operation. I am multiplying the third row by 3. Therefore we get 0 0 3. And then I am adding with the first row. Therefore we get 3 here. So that is it. So this is elementary matrix. So elementary matrix is obtained from identity matrix by executing only one elementary row operation. Okay. So therefore we have to form, given any matrix, we know that how to get a row reduced echelon form, right? So given any matrix A, we have two matrix. One is row echelon form of a matrix. So another one is reduced row echelon form of the matrix. Okay. So given any matrix, we have unique reduced row echelon form matrix and then row reduced echelon form matrix. So how we'll get this one? Usually we have to we know the how to make this one, right? So So this is nothing but actually we have to suppose you take A and then you have to so apply or multiply some elementary matrix. So E1 is some elementary matrix, and then you have to apply multiply with another elementary matrix, so and so on. You get some finite multiple of elementary matrix. You will get a row reduced echelon form or row reduced form. So that is we have to add and subtract the usual one, but so same thing is nothing but just you have to multiply some elementary matrix. So if you take some matrix and then multiply some finite number of elementary matrix, finally you get a row reduced echelon form. Okay. So doing this nothing but just you have to multiply the elementary matrix to the matrix, you will get a row reduced echelon form. Now another definition. So this was always invertible matrices. Okay. Now next definition, permutation matrix. A matrix said to be permutation, you have to permute the columns or rows of the identity matrix. We have to permute the rows of the identity matrix. So that is the next definition for permutation matrix. So definition. So yeah, permutation matrix. So these are all always square matrix. Okay, so permutation matrix. A permutation matrix is a square matrix. Is a square matrix obtained from identity matrix. Obtained from the identity matrix. Identity matrix by permuting the rows. By permuting rows, we can permute first row and then third row, or second row and then fifth row, anything. So you have to permute the rows. Permuting the rows. Such a matrix is called a permutation matrix. Okay. So for example, even some elementary matrices are, suppose if you apply the second kind of elementary row operation. So what is the second kind? You are interchanging two rows, right? So interchanging two rows, it can be actually permute the rows. So first row maybe go to the fourth row maybe comes to the second row maybe go to the first row. So that is just a permutation of the rows. The resulting matrix is called a permutation matrix. So for example, if you take example of some matrix, if you take maybe we call some A, or usually permutation matrix we call P. P means permutation. So I take this matrix 0 1 0 1 0 0 0 0 1. So this is the permutation matrix because I permute the first row and then second row of the identity matrix. Suppose I am taking some other matrix, some P1, another matrix. So I am writing this 1 0 0 0 1 0 3 0 1. This is not a permutation matrix because we have permit only the rows. Now we have extra element 3. 3 is not in the one, right? So therefore this is an elementary matrix because you multiply the first row by 3 and then add to the last row of the identity matrix, you get this matrix. Therefore this is a elementary matrix, but it's not a permutation matrix. But this matrix is not permutation. So permutation matrix, all the entries are either 0 or 1. So no, not other numbers. But elementary matrix, the entries are maybe 1, 0 or any other number. But the permutation matrix, every row contain only 1, 1, or every column contain exactly 1 ones. All others are 0. So it's not permutation matrix. Permutation matrix. So therefore, some elementary matrices are permutation matrices. Again, some all permutation matrices are elementary matrices. Okay, because we apply the second kind of the row elementary operation, right? So therefore, every permutation matrix is a elementary matrix, but elementary matrix need not be a permutation matrix. This P1 is an example for that one. Okay. Now, so this permutation matrix is also again invertible matrices. Okay. So now maybe so you are all familiar with the inverse and then determinant of the matrix. Okay, so maybe I state that when we say a matrix has to be invertible, So suppose if you take A is a n by n matrix, is invertible if we can find another matrix, that is there is another B is an n by n matrix such that the product AB and BA should be identity matrix. A into B and equal to B into A equal to identity matrix, then we say B is the inverse of A. So this is the first definition. You can say a matrix, n by n matrix is invertible. If we can find another n by n matrix B such that AB equal to BA equal to identity, then we say A is invertible matrices. And the theorem, okay, suppose AB equal to identity, then we say B is called left inverse, okay, or right inverse. This B is called so this is actually right side. So therefore this is right inverse of A. So this is happened, then B, this B is called left inverse of A. Okay, left inverse of the matrix A. If both the left inverse, right inverse exist and both are equal, then we say it's a inverse of the matrix. So that is a usual one. Okay. So maybe suppose a matrix is invertible. Suppose we have a system of equations. Suppose we have a system of homogeneous equation, that is Ax equal to 0. In this case, suppose we consider the homogeneous equation and suppose A is invertible. Then the system has a unique solution, that is nothing but x equal to 0 is the only solution. Because you can multiply A inverse both sides, we get x equal to 0. So x equal to 0 is the only solution of this homogeneous equation, Ax equal to 0, provided A is invertible matrices. And A invertible means it should be square matrices. Okay, we can talk about invertible only for square matrix. So these are very important. And suppose if you take triangular matrices, what is the invert? Suppose a triangular matrix is invertible means what? It should be all the diagonals are non-zero entries. So other way you can say. So we can talk. We already. So I assume that you know the determinant definition. Suppose determinant of a square matrix A is not equal to 0, is non-zero if and only if A is invertible. So a matrix is invertible, then the determinant is non-zero. If determinant is non-zero, then the matrix is invertible matrix. Okay. So if a triangular matrix is invertible means what? The determinant should be non-zero. So what is the determinant of a triangular matrix? Is nothing but product of the diagonals. Suppose we have a triangular matrices, maybe suppose either upper triangular matrices or lower triangular matrices. Okay. Suppose we have this is the diagonal elements, and suppose below the diagonals are 0, above the diagonals are some non-zero elements are there. Okay. So what is the determinant of these matrices? Is nothing but just the product of diagonals. Product of diagonal elements is the determinant. Either you can take upper triangular matrices or lower triangular matrices. The determinant of the triangular matrix is nothing but product of the diagonals. So if it is invertible, then the diagonal should be non-zero. Okay. So a triangular matrix is invertible if and only if the diagonal elements are non-zero elements. Okay. So this is one important thing. And suppose if you take a homogeneous equation, non-homogeneous equation Ax equal to B. So again, if A is invertible, and suppose we have equation Ax equal to B, and A is invertible, then again the system has a unique solution. So Ax equal to B and A is invertible. Again, the system have a unique solution. So that solution is nothing but x equal to, we have to multiply A inverse both sides, we get A inverse B. So x equal to A inverse B is the solution. So in a square matrix, again we assume that A is a n by n square matrix. Okay. So if A is invertible, then the system Ax equal to B as a unique solution. If A is not invertible, the system may be either solution, therefore it has infinitely many solution or no solution. Okay. So maybe I state as a theorem for this one. Okay. The theorem says, suppose A is an invertible matrix. If A is an n by n invertible matrix, if A is an n cross n or n by n is an invertible n by n or n by n invertible matrices. Invertible matrix. Then for any column B vector, then for any column vector B. So here they take small b, no need to take the capital B. So column vector B, maybe we can write in the notation B1, B2, etc. some Bn transpose. That means you have to write in column. So now I'm writing a row vector and then take that transpose. So we'll get a column vector. So then the system Ax equal to B as exactly one solution, namely x equal to A inverse B. Okay, so we call that x equal to capital X. If we take capital X, then we can write capital X. Okay. So Ax equal to B has exactly one solution. That solution X is A inverse B. Okay, that is the first one. Suppose if A is not invertible, if A is not invertible matrix, A is not invertible, A is invertible, A is not invertible, then the system has either no solution or infinitely many solution. Either no solution or infinitely many solution. Infinitely many solution. Any solutions according to the consistency of the system. Okay. Okay, so if the matrix is invertible, then the system has any solution. If the matrix is not invertible, either the system has no solution or infinitely many solution. Okay, this is a very important thing. Now I give some some properties of the triangular matrices. Product of triangular lower triangular matrices again is a lower triangular matrices. If A is invertible and A is lower triangular, the inverse also lower triangular matrices. All the things I will leave it to you. So just to go through the properties of lower triangular matrices and then upper triangular matrices. So product of two upper triangular matrices is upper triangular matrices. Inverse of an upper triangular matrix is upper triangular matrices. Similarly for lower triangular matrices. Okay. Now I'm going to define what you mean by null space. Okay. So if we take given any matrix, we already talk about the rank of the matrix. Okay. So before going that, okay, we already discussed the determinant, and then we know the formula for inverse, right? So A inverse nothing but 1 by determinant of A into adjoint of A. So the formula for A inverse, if A is a square matrix, if determinant is non-zero, then we can define A inverse nothing but 1 by determinant of A into adjoint of. So how we will find the adjoint? You want to take the cofactor of each element and then take the transpose. You will get a adjoint of A. Now maybe I can write some properties of determinant. So suppose if you have in a matrix two rows are identical or either one rows are zero, the determinant is always zero. And then maybe I can the first properties of determinant I can write. So here, suppose if a matrix, a square matrix, if A has either zero row, suppose a matrix contains zero row, either a zero row or two rows are identical, or two identical rows, then the determinant is zero. Then the determinant of the matrix is zero. Det of A is zero. Either the matrix contains zero row or two rows are identical, then the determinant is zero. Okay, that is the first one. Suppose if take the determinant of product of two matrices, that is determinant of A into B, both A and B are square matrix n by n matrices, then the determinant of A equal to determinant of A into determinant of B. is very important property, but sum is not true. That is, the determinant of a plus b need not be equal to, so determinant of a plus b need not be equal to determinant of a plus determinant of b. Why? Because if we take some simple case, if we take a 2 by 2 matrix, I'm writing here. Suppose if we take a first row is 1 0, for this example, if we take first row is, I'm taking a equal to this. I'm taking b equal to 0 0 0 1, this matrix. So if you add these two matrices, you get identity matrix 1 0 0 1. Okay. 1 0 0 1. But what is the determinant of this 1? What is the determinant of this matrix 0? What is the determinant of this matrix 0? But sum not equal to 1. Therefore, determinant of a plus b not equal to determinant of a plus determinant of b. But sum maybe is true for some special type of matrices, but in general is not true. Now the fourth property, suppose you are multiplying a scalar to the each element of the matrix. So suppose I am taking, so determinant of some scalar small k times a matrix A is equal to, if we take k outside, we get k power n, where n is the order of the matrix. Suppose A is a n by n matrix. We suppose to find the determinant of Ka is nothing but k power n into determinant of A. Okay, where k is any number, maybe positive or negative. Okay, if it is 0, that is trivial. If k equal to 0 means what? You are multiplying 0 to all the term, it becomes a 0 matrix. So determinant of 0 is 0. Okay. So this is very important properties of determinant. Okay. Now, and then one more thing. So the determinant of the transpose of the matrix same as the determinant of the matrix. So determinant of A transpose is same as determinant of the matrix A. Is always true for any square matrix. Determinant of A is same as determinant of the original matrix. Suppose if we take triangular matrix, the determinant of the triangular matrix is nothing but product of the diagonals. Okay, that is also very important. So the determinant of the triangular matrix. So determinant of a triangular, maybe upper triangular or lower triangular, anyway triangular matrix. The determinant of the triangular matrix is the product of diagonal elements. Product of the diagonal elements. Even if you take diagonal matrix, the determinant is nothing but again product of diagonal elements. Okay, so these are all very important properties of determinant. Okay, so maybe and maybe one more method is there to find the determinant of a 3 by 3 matrix. So you know very well to determine the determinant of the matrix. You have to expand either row wise or column wise using cofactor. You will find the determinant. So one more method is there to find the determinant of a 3 by 3 matrix, particularly for 3 by 3 matrix. So that method is called as Sarus method. Sarus, Sarus method. So this method is finding the determinant of a 3 by 3 matrix. So what is the method says? Suppose we have a 3 by 3 matrix. Okay, maybe I can write here. Suppose we have a 3 by 3 matrix. A1, B1, C1, A2, B2, C2, A3, B3, C3. We have to find the determinant of these. Okay, so suppose I am taking this is our matrix A. A equal to this. So usually how we'll find the determinant of A? So determinant of A equal to, first we have to keep A1 and then the determinant of the remaining cofactor, that is B2, C2, B3, C3, and then minus B1 times the remaining things A cofactor of this A2, C2, A3, C3, plus the last term C1 times the cofactor of C1 is A2, B2, A3, B3, and then you can simplify these, you will get the determinant. Now the Sarus method says you have to first write the all matrices. So A1, B1, C1, and then A2, B2, C2, and then A3, B3, C3. Now again you got to start A1, A2. You have to write the first column A3, and then you have to write the second column B1, B2, B3, and you stop. Okay, no need to write the third column. Now this is a I think 3 cross 5. Anyway, don't worry about that. So now we have a diagonal. So this is a one diagonal. Okay, so we have to multiply all these number. So and then we have another diagonal. So these diagonal elements you have to multiply and then sum, and then this is another diagonal. You have to multiply all these three elements and then sum this number. So this is actually plus and this also plus. You have to multiply this number and then add with this and then add with this, minus you have to subtract this diagonal. So you have to multiply these three diagonals and then you have to multiply these three elements and then we have to multiply these three elements. You have to multiply and then subtract minus of this one. Okay, so this is the determinant of the 3 by 3 matrix. So in the leading diagonal you have to multiply and then sum, and then you have to subtract this diagonal, off diagonal. So you will get a determinant of the matrix. For example, if we take some special matrix 1 1 1 1 1 1, so if we take everything is 1. Now I am writing the first column, I am writing the second column. So anyway, our matrix is original matrix is 3 by 3 matrix. Now what is the product of this is 1 into 1 into, so all the products anyway 1, therefore 1 plus another diagonal is 1 plus 1. So these are all off diagonal value minus again everything 1, minus 1 minus 1 minus 1 is nothing but therefore 3 minus 3 equal to 0. Therefore the determinant of this 3 by 3 matrix is 0. So the Sarus method is useful to find the determinant of a 3 by 3 matrix. Okay, so you have to multiply the off diagonal elements and then sum. You have to, and then you have to subtract the leading diagonals. You have to multiply and then sum. And then off diagonal elements you have to multiply and then subtract. So you get a determinant of a 3 by 3 matrix. Okay, so this is Sarus method. So for higher dimension, for example, suppose if n, any n where n is greater than or equal to 3, so we have a formula, or you have to use the usual method, or there is a formula to find the determinant of a n by n matrix. Okay, so suppose we have a n by n matrix, A is an n by n matrix. Now the determinant of A, we have a formula is that summation all permutation sigma varies on the symmetry group Sn sine of sigma, because the sign may be either plus 1 or minus 1 depending upon sigma. If sigma is an even permutation, then we get plus. If sigma is an odd permutation, we get minus 1 into A1 sigma of 1, where sigma is a function from the one element, n elements is to 1 to n, right? So A2 sigma 2. The first row you can take the image of the second suffix and so on, product with the an sigma n. This summation ranges over all permutation. Okay, and then you have to take the this thing. Okay, for example, if you want, maybe I will give one short. So we are not going to use this formula for any problem solving, but you should know the formula to find the determinant of any n by n matrix. Whereas what do you mean by Sn? So Sn is the collection of all functions from the set 1 to n elements to 1 to n elements, and the sigma should be bijection. All bijection function from the set In means what? Is a contains, don't this is not an identity matrix, this contains 1 to n elements. So set of all function from this set to this set and bijection, we collect this form a group with respect to composition, and then the summation varies over all permutation into sigma sign of sigma, and then A1 sigma 1, A sigma 2, and so on, A sigma 1 n. So this is another method to find the determinant. Okay. Now all the things we discussed about the determinant. Yeah, if you have any doubt, you can ask.
Sir, how to use this formula, sir?
Yeah, maybe I will give one example. If you take 3 by 3 matrix, okay. So first of all, we should know what is this Sn. So Sn is we call actually symmetric matrix or permutation group. Okay, symmetric groups are permutation group. For example, if you take n equal to 3, S3 we denote S3 is nothing but all functions from the elements from 1 to 3 element sets to 3 element sets. So I am directly write identity. So identity means what? 1 goes to 1, 2 goes to 2, 3 goes to 3. That is identity. And then 1 goes to 2, 2 goes to 1, but 3 goes to 3 fixed. And 1 goes to 1 is 1 goes to 3 and then 3 goes to. So that means what? Suppose we have a domain have 3 elements 1, 2, 3. And then codomain also have a three elements 1 to 3. How many functions we can define from this to this with the condition that the function should be bijection function. So bijection means what? Should be 1 1 and on 2. So 1 1 means what? Different element in the domain maps to the different element in the codomain. On 2 means what? If we take any elements from the codomain, there is a pre-image. So what do you mean? Identity means what? So I am one function is 1 goes to 1. I am defining 1 maps to 1, 2 maps to 2, 3 maps to 3. That is I am defining E. Okay, that is the identity permutation, identity function. Okay, the next one 1 comma 2 means what? So that is the element 1 maps to 2. That element 1 maps to 2. I am assigning this element 1 to 2 and then 2 to 1, but 3 is fixed. 3 is I am not mentioning here. That means what? 3 goes to 3. So this is another function. This is also 1 1 and on 2. I am denoting this function is 1 comma 2. That is 1 maps to 2, 2 maps to 1. And then 1 maps 1 comma 3 means what? 1 maps to 3. So 1 comma 3 means what? Is a permutation notation. So that means we assign the element, we map 1 to 3 and then 3 to 1. There is no information about 2 means 2 goes to 2. We got to assign 2 goes to 2. So this is also a function. Every element from the domain maps to different element is also on to function. Therefore, it's bijection. Therefore, we call 1 3. Okay. So therefore, the next one is 2 3. So comma 2 3. So 2 3 means what? 2 maps to 3, 3 maps to 2, and then 1 maps to 1. So now all 2 pairs are over. Next, we take 3. So I am taking 1 goes to 2. 1 maps to 2, 2 maps to 3, 3 maps to 1. So I am done this. Suppose 1 maps to 3, 3 maps to 2, and then 2 maps to 1. So this is, so to actually in general, in Sn, what's the cardinality of Sn is n factorial. Okay, the number of elements in the set is n factorial. Here S3, therefore what is the cardinality is 3 factorial. So 3 factorial is, but 6, there are 6 elements. So already we have 1, 2, 3, 4, 5, 6. There are 6 elements. Now, if you take any 3 by 3 matrices, so the determinant is what? So now maybe if you take general any 3 by 3 matrix. So this is actually S3. So S4 means there are 24 elements. That is 4 factorial elements. Okay, for example, now if you take some matrix, special matrix, any 3 by 3 matrix. Suppose I am taking A equal to some any matrix 1, 2, 1, 3, minus 1, 2, 0, 5, for example 4. So I am going to find the determinant of this matrix using that formula. So first, so therefore determinant of A is nothing but by formula summation of sigma, summation runs over the all permutation Sn, but instead of here Sn is S3 and sign of the permutation. I will define what is the sign. Okay, so into A1 sigma 1 into A2 sigma 2 and then A3 sigma 3, because we have only 3, because in the case n equal to 3, therefore we have only 3 permutations. Now what do you mean by sign of a permutation? So if you take any permutation, the sign of the permutation sigma is either 1 or minus 1, only 2 values. So when it is minus plus 1 if sigma is even permutation. So what do you mean by even permutation? I will tell. So if sigma is odd, the sign is minus 1. So when we say a permutation is a even permutation, actually this actually say length of the permutation. So here if you take the first permutation 1 2, So here length is 2. Here also length is 2. Here also length is 2, but here the length is 3. Here the length is 3. So usually we call this is cycle notation. If you write this actually cycle notation. So the length of the cycle, this is a 3 cycle. This is also a 3 cycle. This permutation is 3 cycle, but this is a 2 cycle. Actually, you call the 2 cycle is transposition. Transposition. So transposition, nothing but the length of the cycle should be 2. Okay, so that is the definition for transpose. So transposition of a permutation, nothing but the length of the permutation is 2. Then we call that permutation is transposition. Otherwise, we call cycle. So this 1, 2, 3 is a 3 cycle because length is 3. Therefore, this is 3 cycle. This is also 3 cycle. We call this is 2 cycle, but we define 2 cycle is transposition. Okay, now we define this even permutation. So this all comes under algebra, but anyway. So suppose we say sigma is even permutation. Even permutation. If the sigma can be expressed, can be expressed as a product of even number of transposition, as a even number of transposition. Okay, even number of transposition. That means what? So if you take 1, 2, so this is sigma. So sigma can be written as just 1, 2. We have how many? Transposition? We have only one because there is namely 1, 2. Therefore, this is the odd permutation. Otherwise, odd permutation. Okay. So otherwise, that is, if you suppose a permutation can be expressed as an odd number of transposition, we call it an odd permutation. If a permutation can be expressed as a product of even number of transposition, we call it even permutation. Otherwise, odd permutation. So, but the theorem says any permutation can be expressed as a product of transposition. Any permutation can be expressed as a product of transposition, the theorem says. For example, for first 3 elements, not a problem. If you take 1, 2, 3, how to write this 1, 2, 3 permutation is a product of transposition is that. So just 1 goes to 2 into 1 goes to 3. So that's it. Just 1, 2, 1, 3. Okay. Otherwise, somebody says 3, 1, 3 to reverse, but this also true. So therefore, this permutation can be expressed as a product of transposition, nothing but 1, 3 into 1. For example, in general, suppose we have A1, A2, A3, A4 like this, then we can be written as this as A1, A2 into A1, A3 into A1, A4. Okay. So this is a, because length is 2, therefore this is transposition, this length is 2, therefore this is transposition, this is also length 2, therefore transposition. Therefore this permutation or this cycle can be expressed as a product of transposition. If the number of transposition in the product is even, then we say this is even permutation. Now look at this, we have 1, 2, 3. 3 is the odd number, therefore this permutation can be expressed as odd number of transposition, product of odd number of transposition, this is odd permutation. Look at this is even, 1, 2. There are 2 transposition, therefore this is even permutation. I simply say the length is odd, suppose the cycle length is odd, this is even permutation. If cycle length is even, because 4 is a even, if length is even, we say it's odd permutation. We can say anything. Okay. Now we know the definition of signature of, that is sign of even permutation. Now, so the identity permutation always even permutation, therefore this is plus 1 sign. Okay. So what about others? This is minus 1 because only one transposition, therefore length is only one transposition, therefore sign is 1. Sign of this one is minus 1. Sign of this also minus 1. But sign of this is 1 because it's an even permutation. Sign of this also 1. Okay. Now I erase this definition of sign. Now we have to uh, run the summation over each permutation. Okay, first you take the identity permutation. Okay, that is sine of identity permutation E. So E means what actually? So E means what? The notation, this bracket 1, bracket 2, bracket 3. That means what? 1 maps to 1, 2 maps to 2, 3 maps to 3. Okay. Okay. Now therefore sine of identity permutation here E of 1. So E of 1 is 1. Therefore A1 1, A1 A2 2. Okay. I think I did mistake. This is actually 1 1, right? So this is actually 1. This is also 1. By the formula, this is A1 sigma 1. Here, there also I did mistake, right? Oh, okay, okay, I correct. So 1 sigma 1, 2 sigma 2, right? Correct. So I am ready correct one. Okay, correct. Now A1 1, because now I am taking identity permutation. Here sigma equal to identity. Therefore, identity means 1 maps to 1, 2 maps to 2. So here, therefore A1 1. So here A2 2. Here A3 3. Okay, A3 3. Plus I am taking the next permutation sine of what is I am taking the next permutation from the group 1 2. Okay, so sine of 1 2, that means 1 goes to 2, 2 goes to 1, 3 is fixed. So therefore now here sigma equal to 1 2, therefore substitution the formula, what is you will get A1 sigma of 1, but what is sigma 1 maps to 2, therefore A1 2. A2, what is sigma of 2, 2 maps to 1, therefore is 2 1, and then 3 is fixed, that is 3 goes to 3, therefore A3 3. Now we did the another. Now we take 1 3. So sine of. So here what is A1 1? Usually this position in the matrix. This is actually A1 1 position. This position is A1 2 position. This position is we call A1 3, first row, third column. So this position is called A2 1, and this is A2 2, and this position is A23, okay, and so on. So this 0 is A31, and this 5 is A32, this 4 is A34, A33 position. Okay. Now and so on. You can take another plus sine of another permutation is 1 3. So that means 1 maps to 3, 3 maps to 1, but 2 is fixed. Therefore sigma of 1, sigma of 1 is 3. A2 sigma of 2, sigma 2 is fixed, 2 is fixed, and sigma of 3, sigma of 3 is 1. Now we did the sigma of 1. Now sine of next one is 2 3 permutation in the group, that is 2 maps to 3, 3 maps to 2, therefore 1 is fixed, therefore A1 sigma 1 is 1, and A2 sigma 2 is 3, but sigma 3 is 2, therefore A3 sigma 3 is 2. Now you have to find, and then what is the next permutation? Sine of the permutation 1 2 3, that means 1 goes to 2, 2 goes to 3, 3 goes to 1, therefore A1 sigma 1, sigma 1 is 1 goes to 2, therefore 2. A2 sigma 2, sigma 2 is 3, into A3 sigma 3, sigma 3 is, we finish the cycle, that is 1. So the next sum is, the last one is sine of the last permutation 1 3 2. This is A1 sigma 1, 1 goes to 3. A2 sigma of 2, sigma of 2 is 1. A3 sigma of 3 is 2. Now we have a 6th term. Now substitute the values, you will get. So now maybe erase here. So sine of identity permutation is 1. Okay, therefore this is 1. Therefore 1 into, what is A1 1? Nothing but 1. A2 is minus 1, minus 2 in the diagonal. So look at the diagonal. So these are all everything diagonal elements. Take the product. 1 into minus 1 into 4 is minus 4. Therefore this product is minus 4. Right? Plus sine of 1 2. Sine of 1 2 is, already we know that this is minus 1. And what is this product? A1 2, A2 1, A3 3. So look at this matrix. A1 2 value is 2, A2 1 value is 3, A3 3 value is 4. Okay, into 4. So that is 12 and then 24. So this is actually 24. Therefore we erase this term. We find the value of this. Now the next term, sine of 1 3. Sine is again 1 3. The sine is minus 1. What is the product? A13. A13 value is 1 into A22 value is minus 1 into A31 value is 0. Therefore 0 into anything 0. Therefore this product is 0. Okay. Therefore we cancel this term. We did it. Now this term, again sine of 2 3. The permutation sine is an odd permutation. Therefore sine is minus 1. And what is the value of A11 is 1. A1 value is 1. A23 value is 1. A32 value is 5. Therefore 1 into 5 is 5. Therefore into 5. Okay, we did this part. So maybe I erase it. Now we did this one. Now sine of 1 2 3. So sine of 1 to 3 is 1 because it's a odd permutation. Sorry, even permutation. 1 2 3 is a even permutation. Therefore the sine is 1 into A12. What is the value of A12 is 2. The matrix is 2 into A23 is 2. And then A31 is 0. Therefore totally we get 0. Therefore we did this part. Now the final one is sine of 132 is a even permutation. Therefore sine is 1. And then what is the value of A13 is 1 into A21. A21 is 3 into A32 is 5. Therefore 15. So now just to simplify, you will get the determinant. So for that you should know about the symmetric group Sn. Okay, S3 means only contains 6 elements, but Sn contains 4 factorial, 24 elements, all the things. So in general Sn, the number of element in Sn is n factorial. Okay, now simplify this equal to 1 into minus 4 and minus 24, and this is 0, and then this is minus 5, and this is 0, then this is plus 15. So how much? This is actually 30 minus 34, 28, sorry, 33, yeah. 33 plus 15. Okay. Now how much? This is 15, 18, right? Minus 18. So this is the determinant. Okay. So this formula can be used to find the determinant of higher order. Okay, but in hand it's very difficult to do. But for 3 by 3 matrix we can use this formula. Otherwise we have to write some algorithm or programming to find the determinant of any matrix. Okay. Anyway, I will tell something. So easy method to find the determinant of the matrix. Okay, for anything, but we need some extra information about the matrix. We will discuss about later. Okay, now we discuss about the determinant. Okay, and then we discuss about the properties of the determinant. Okay, good. So for any doubt you can ask. And there are some important matrix are there. So in examination usually they will ask that matrix. That matrix is actually called Wanderman matrix. Okay, Wanderman matrix they will call. Okay. Now what is the mean by Wandermonde matrix? So how the matrix look like is the first column should be 1 1 1, or you can write some other thing. It should be any order. Okay, it should be square matrix. Suppose if you take 1 1 1 4 by 4. Okay, so 4 row, then 4 column. Suppose I am taking some x, then it should be x square and should be x cube. And if you take any other variable y, and this should be y square and this is y cube. If you take z, then this should be z square, should be z cube. And this is, suppose you take w, and this should be w square and this is w cube. So this is a Wanderman matrix. Okay, so usually we call A. So what is the determinant of this matrix? Actually, if you simplify, you can apply the rules. You can subtract, you can simplify this matrix. Okay, row reduced echelon form, finally you get something. So directly I can write, so determinant of the matrix is nothing but, we have to subtract from this, so x minus y, and then x minus z. You have to fix x and then subtract each term, x minus z, and then x minus w. Once you did the first one, now come to the second variable, y minus z, and then y minus w. Now with the y, now come to the last one, z minus w. That's it. So this is the determinant of the van der Waals matrix. So van der Waals matrix look like this one, 1 1 1, x y z, x square y square z square w square, x cube y cube z cube w cube. Okay. So any matrix of the form, this is nothing but van der Waals matrix. Suppose maybe sometimes the matrix may be given like this, 1 1 1 1. Okay. X square x cube, y square y cube, z square z cube, w square w cube. So this also van der Waals matrix. It's nothing but just transpose of this matrix. And we know that determinant of the matrix and determinant of the transpose are the same, right? Therefore, determinant of this matrix also the same thing. X minus y, x minus z, x minus w, and then y minus z, y minus w, z minus w. Okay. So it's very important matrix, and this is very important formula. Just to subtract, fix one and then subtract others. Okay. Okay, this one is very important matrix. And we know the formula for adjoint of the matrix, right? So what we know about A inverse. So the A inverse equal to 1 by determinant of A times adjoint of A. Okay. Now we can write what is the, from this we can take adjoint of A one side and then take the determinant, we can cross multiply the determinant. Therefore we get adjoint of the matrix A equal to determinant of the matrix into A inverse. So this is the relation we will get. Just to cross multiply the determinant, we get this one. Now this is the determinant adjoint of A. What about adjoint of A inverse? For that, what is the determinant of A inverse? So determinant of A inverse is nothing but 1 by determinant of A, provided the determinant is non-zero. Because otherwise we cannot, we will not speak about this A inverse. So determinant of A inverse is nothing but 1 by determinant of A. This is very trivial because we know that A into A inverse is identity, always identity matrix. Now apply determinant both side, determinant of A inverse equal to determinant of identity matrix. So determinant is the identity matrix is a diagonal matrix, therefore determinant is the product of diagonals, we get 1. And we know apply the determinant of product of the matrix nothing but determinant of A into determinant of A inverse. Apply the properties of determinant equal to 1. Now keep determinant of A inverse one side and then we will get determinant of A inverse equal to 1 by determinant of A. It's very important property. Now we get relations, we get definition of adjoint of A. So adjoint of A is nothing but determinant of A into A inverse. Now what is the adjoint of A inverse? Adjoint of the matrix A inverse. Now substitute A by A inverse. That's it. What will get? It's equal to determinant of A inverse and then A inverse whole inverse. So A inverse whole inverse nothing but A. Therefore A into, and we know that determinant of A inverse, just now we show that is 1 by determinant of A. Okay. So we will get this is nothing but actually A by determinant of A is nothing but adjoint of A whole inverse. Why? Because adjoint of A we know this. Okay. Adjoint of A is nothing but this. Now if you take inverse both sides, if you take the inverse both sides, therefore adjoint of A whole inverse equal to determinant of A into A inverse whole inverse. Therefore, determinant is a constant. Therefore, determinant inverse is nothing but 1 by determinant of A. This is because of constant. But what is A inverse? Whole inverse is nothing but A. Therefore, A by determinant of A is nothing but adjoint of A whole inverse. Therefore, what we prove now, here is this: adjoint of A inverse equal to adjoint of A whole inverse. So now there is a relation between adjoint of A and then adjoint of A inverse. So what we put, adjoint of A inverse is adjoint of A whole inverse. These properties are very useful to solve some problems. So now we find the adjoint of A inverse equal to adjoint of A whole inverse. Now the another property is that, suppose I assume that A is invertible, determinant of adjoint of A. What is the determinant of adjoint of the matrix A? And we know the adjoint of A formula. So adjoint of A is nothing but this thing. Okay, this is the adjoint of A. Now apply determinant both the side. So determinant of adjoint A equal to determinant of A inverse. So determinant is this is scalar. You can take outside from the determinant. Therefore, determinant power the order of the matrix. Suppose I assume that A is the n by n matrix. You will get, I'm directly write it here. So this is nothing but determinant of A whole power minus n minus 1. You can easily prove it. Just apply the determinant both side, and then so maybe if you want, maybe I can quickly prove it. So now apply determinant both side to this equation. So what you will get? So determinant of adjoint of A equal to determinant of the full things, that is determinant of A into A inverse. But determinant is a constant scalar. You can take outside, but if you come outside, it should be determinant of A power order of the matrix. What is the order of matrix? Is n by n matrix, therefore power n. Now we get a determinant of A inverse. But determinant of A inverse is nothing but 1 by determinant of A. We can cancel one determinant. We get determinant of A power n minus 1. We can cancel one determinant. So that's we get. Determinant of adjoint of A is nothing but determinant of A power n minus 1. So this is the one thing. And what is the adjoint of the matrix adjoint of A? So that is adjoint of A. So any matrix we can talk about the adjoint. So what is the adjoint of adjoint matrix? Is nothing but determinant of A power n minus 2 times A. You can easily proceed using the formula adjoint of A. Okay, you will get it. And then the another properties of adjoint. So what is the product of adjoint of two matrices? That is adjoint of the matrix, product matrix AB is equal to actually adjoint of B, reverse adjoint of B into adjoint of A. This properties are very important. It's a reverse property. So adjoint of AB equal to adjoint of B into adjoint of A. Okay. Suppose we have a matrix like this. Adjoint of a matrix is of the form some Q A Q inverse. Then this is nothing but we can take the adjoint inside. Therefore, we get Q times adjoint of A into Q inverse for any invertible matrix. Okay. The next property of adjoint, if we suppose A B equal to B A, suppose we have a two matrices A and B satisfy the commutative property. Suppose A B equal to B A, then what is about the adjoint? So then adjoint of A into B equal to B into adjoint of A. So these are all properties of adjoint. You should remember this. Okay, and then you know Grammar's rule to find the solution of the system of equation n by n matrix. Okay, so therefore I don't want to discuss that. Okay, using you already studied in school days or in UG grammar rules to find the solution of the equation. Okay. Now, actually, plan. So, in general, geometrically, what do you mean by this determinant? So, if you take 2 by 2 matrices, So the determinant is nothing but area of the parallelogram. If you take 2 by 2 matrices, okay, so what is 2 by matrices? If you take A, B, C, D, in geometrically, maybe sometimes they will ask. So what do you mean by, suppose if you take 2 by 2 matrix A, B, C, D. Okay, so A, B, C, D is our matrix A, and we know the determinant. So determinant is nothing but the number AD minus BC. But what geometrically, what is this represent this determinant? So actually determinant is nothing but is a area of the parallelogram. So suppose we have a plane here. Suppose consider the first row as a pair. Suppose this is A comma D is the first one element. And suppose if you take some other element, this is another row, that is C comma D. Okay, C comma D is the another one. So they form a parallelogram, something like this. Okay, so if you take the sum, and take the sum of this should be the diagonal. If you take, suppose this is the one vector, maybe you call X, and this is Y, then X plus Y should be here. So this is X plus Y usually. Okay, so we form a parallelogram. So area of this parallelogram is nothing but actually the value AD minus BC. So that is, so the determinant of a 2 by 2 matrix ABCD represents the area of the parallelogram of the corner of the vertices ABCD. Okay, this is for only 2 by 2. In general, is nothing but suppose we take 3 by 3 matrices. What do you mean by determinant of the matrix in geometrically is the volume of the that diagram. If you take 3 by 3, you will get something volume. So you got to find the volume of this one, surface. If you get some surface, the volume of the surface is the determinant. For 2 by 2 matrix is the area of the parallelogram. Okay, so you should know, remember this. What do you mean by geometrically? What is the meaning of what the determinant represent? Okay. Maybe I stop now. Next class we will introduce what is nullity, all the things. Okay.